Okay, so for this last lecture, we shall study Gibbs sampler in depth. So the Gibbs sampler, the name comes from the Gibbs distribution, as we discussed before, and it really should be called iterative conditional sampler. So let me again start from a background in probability theory, in particular conditioning or conditional distribution. So last time we briefly mentioned the idea of conditioning. That is, you pay attention to a subpopulation when you sample from a population, or you just focus your attention to a subspace for the whole sample space. So this is idea for conditioning. So for the discrete case, let's imagine that we have two random variables x and y, and we can imagine that we have a unit square like this one. So this unit square, so the coordinate is u1 and u2. But if we have two discrete random variables, x and y, for example, x is an eye color and y is a hair color of a random person, and we can assume that there's four different eye colors and four different hair colors. For example, the eye color may be black or blue, hair color may be black or blonde or some other categories. So, and then you can imagine that if we randomly sample sample a person from a population, then it is like we randomly sample a point from the unit square, or rather, we randomly throw a point into this unit square. And suppose that according to the probability distribution of x and y, we can actually partition the unit square in this way, so that for x we have 1, 2, 3, 4. So each x corresponds to a column. And for y, we also have 1, 2, 3, 4, so that each y corresponds to a row. So I just make this arbitrary shape. So we want to get the intuition about the joint distribution and the marginal distribution, and more importantly, the conditional distribution. So here, if you randomly throw a point into the unit square, the probability that you throw into a cell for x and y, for example, x equal to 3, y equal to 3, which means this cell. So this is proportional. This probability is proportional to the area for this cell, right? So this gives us a notion of joint distribution. So that is the joint distribution of a cell xy, or the joint distribution for these two values x and y, where x can be from 1 to 4, y can be from 1 to 4, is really just the area of the cell of xy. So if x equals 2 and y equals 4, then we are talking about the area of this cell. Because according to axiom 0, the probability that we throw into the cell xy is proportional to this area, right? And then we return the corresponding value of xy. So therefore, the joint distribution of xy, or the joint probability mass function for xy, denoted by pxy, small x, small y. So this equal to the area of the cell of xy under this uniform sampling or equal likely sampling. And then if we look at the marginal distribution, so suppose you randomly throw a point that asks you what's the probability that x, random variable x equal to, say, 3, and then you only need to look at the area for the column. So the column for 3, right? So that is the probability mass function for x. So here I use P sub capital X. So this is a whole notation to denote the marginal distribution of x. But if, based on this context, if you put small x here, based on this context, it is actually clear. you are talking about the marginal distribution of x. So you don't need to add this x if you feel that you are not going to get confused. And then that will be simply just error, again, according to axiom 0. So that will be the error for column x. And clearly that will be this column of this x will be the summation of all those cells, sum over all possible values of y. So summation y pxy, right? And similarly, pyy is equal to summation of the joint over x. So this is our first operation when we deal with multiple random variables. So that is this is marginalization. So if you want to find the marginal distribution for a variable, you just sum over all the other irrelevant variables. And this can be easily seen as the error for this column is a summation for the error of those cells. And under uniform sampling, equal likely sampling, so the error gave us the probability because the total probability is 1. So this is marginalization. Now, for operation 2, the second operation, so we have the conditioning. So we use, again, this is whole notation, P for capital X given capital Y. So this means the conditional probability mass function of Y given X equal to small x. So what's the meaning of that? So that is, suppose I tell you the value of random variable x equal to this small x. For example, x equal to 3, x equal to 3. If I tell you x equal to 3, so that means the point fall into column 3. And then I ask you what's the distribution of y. Then if I tell you the point fall into column 3, you can reimagine the experiment as you randomly sample a point uniformly from column 3 instead of the whole unit square, or you randomly throw a point into column 3 instead of the whole unit square. And then now you focus on, say, this column 3, then what the distribution of y, or the probability fall into each of the small cells. In this case, our whole sample space become column 3, right? And we can still use axiom 0. So for example, the probability y equal to 3 within this column 3 will be this error divided by the total error, right? So that is given the condition, we simply change the sample space from unit square to this particular column, and then we compute the probability within this new sample space, again, according to axiom 0. So it will be this error divided by the total error. Now the total error become the error of this column 3. So in general, then the probability that you fall into y, given that x equal to small x, which means you sample from this column x, and then the total error of column x is px, and then the error of the cell xy is pxy. So therefore, the conditional distribution or the conditional probability that you fall into y equals y given capital X, the random variable x equal to this small x, is this error divided by this error, because both probabilities are errors of cells and error of column, respectively. Okay, so and then this gave us the second important operation called conditioning. So if you condition on x, then that means your sample space become column x. And then within this column x, you look at the probability. So you get pxy divided by px. So this conditioning is based on this notion of this symbolic idea that conditional distribution equal to the joint distribution divided by the marginal distribution. Okay, so I hope that I give you a most intuitive explanation for these operations. So that is when you randomly sample a point or randomly throw a point into this unit square, So if I tell you x equals 3, for example, then you reimagine that you randomly throw into column 3, and the probability it fall into, for example, this piece, so that y equal 2, then it will be this area divided by the total area for column 3. So that will be P2, 3 divided by P for x3, right? So that's how we think about this. Because I believe that under this uniform equal likely sampling, then we have very compelling common sense about probability, and the conditional probability is nothing but regular probability, except that we now change our sample space from the original sample space to a subspace defined by the condition. Okay, so that's the basic idea. And then we have our second important operation, condition, which means conditional equal to joint divided by the marginal. And then from this property, we see that then Pxy is simply Px times Py given x, right? So the simple operation gives us the third operation, which is factorization. So that is Pxy equal to Px times Py, Py given x. And by the same token, it is also Py times Px given y. So here I did not attach this say x here or y given x here, because based on the arguments, it is clear from the context what we are talking about, right? This is marginal, this is conditional. So this is a factorization. So from here, you see that we may think of x happen first, or x is like a cause, y is like an effect. So x happen first, and then y happens caused by x. So we look at this probability. But from the geometric perspective, then Pxy is area of cell xy, Px is area of column x, and Py given x is area of xy relative to the area of column x. So you see this clearly, you have the identity. Similarly, you have this identity. Okay, so this is a factorization, which means joint can be factorized as a marginal times conditional. And again, conditional, say y given x, you can reimagine that you randomly throw a point into x, which means you change the sample space to x. And a lot of machine learning calculations or calculations in probability or statistics are actually based on the three operations, that is marginalization, conditioning, and factorization. And they can be easily generalized to the situation where you have more than two random variables. So you may have multiple, three or even more random variables, and you can still apply the three operations to do all the calculation. And the three operations are also very easy to remember, to memorize. So then in the future, you do not need to go back to that plot, this uniform unit square plot, in order to do the calculation. Nonetheless, for the purpose of understanding those formulas or build a foundation for your intuition, I think the previous plot is quite useful. And of course, you can also have a new perspective for the unit square plot for the discrete case. So this new perspective is based on hypothetical repetition, or you just repeat the experiment a lot of times, which means you repeatedly throw point into the unit square. And then if this number is large, you repeat a large number of another trace trials. You repeat a large number of trials or experiments. Then Pxy can be interpreted as how often the point fall into the cell xy, or in other words, you look at what the proportion for the points belong to cell xy. So this proportion clearly should equal to the area, right? The bigger the area, the more points you have. And because the total area is 1, so then this proportion is a probability, which again, in this case, we also have very compelling common sense or intuition that the number of points should be the same, the proportional to the size of this cell, right? And similarly, Px, marginal distribution, can be interpreted as how often the point fall into column X, which means what's the proportion of the points that belong to column X. Similarly, Py will be the proportion of the points that belong to row Y. And all those proportions or frequencies are proportional or equal to the area, right, the corresponding area. So that gives us another new perspective for this discrete case. And then you can also interpret the conditional probability of Y given X as when the point fall into X, then how often it also fall into Y. Or in other words, we can also say among all the points that fall into X, say X column, what's the proportion of the points that fall into the XY cell? Okay, so therefore, because see, you either use when it fall into X or among all the points fall into X. So conditioning on X can be interpreted as among all the points fall in X, not among all those points in the unit square, but among all the points fall into column X, then what's the proportion of those, how often it fall into the cell XY. So therefore, it's clearly Pxy divided by Px. I hope that this provides another intuition about this conditional probability based on repetition of the frequency. In particular, Pyx gave us the relative frequency, right? So the frequency of Pxy, but divided by this P of X, in this case, Py given X. So it is a relative frequency. Again, I think this is also a compelling intuition about the conditional distribution by thinking about repeating the experiment a lot of times, and then think about frequencies or relative frequencies, so that probabilities or conditional probabilities manifest themselves in the long run repetition as frequencies or relative frequencies. Okay, so now let's look at the Gibbs sampler. So we are ready to study the Gibbs sampler. Oops, I think somehow this is blocked in my view. Okay, so I also mentioned an example for conditional probability of alarm given fire. So that should be very close to 1, right? But the probability of a fire given alarm is very close to 0. Again, you can think of this as relative frequencies. So that is when there is a fire, how often you should hear the alarm. It should be near 100%. But based on your experience in UCLA, when there is an alarm, then how often there is a fire. So this is close to 0. So this gives you a intuitive interpretation of conditional probability. And also we see that if we exchange X and Y, the conditional probability can be totally different. Okay, so now we are ready to come back to this Gibbs sampler. Suppose we want to sample from Pxy. So we generate Xy from Pxy. And then the algorithm according to the Gibbs sampler is you start from x0, y0. For example, x equals 1, y equals 1. That will be your x0, y0. And then you iterate for t from 1 to until capital T. So in each iteration, you go over 2 steps. So in the first step, you sample xt, you update the value of x from the conditional distribution of x given the current value of y, which is yt minus 1. That's from the previous iteration. And the step 2 is that you sample y, you update y from the conditional distribution. There should be p here, probability of y given the current value of x. The current value of x is xt because you already update xt. And then you go to second step, right? So you keep doing that until you reach this t. So hopefully at capital T, suppose t equal to 1000, then xt, yt that you sampled from this distribution Pxy. And we can continue to use our unit square plot to illustrate this point. So suppose that we want to sample from a distribution Pxy, where Pxy is the same as area of cell xy. Then in order to do that, supposedly you should have a point randomly sampled from the unit square, or you randomly throw a point into the unit square. So you look at the corresponding column and row, and then you get x value and y value, right? That's how you do that. And suppose we follow the Gibbs sampler. So we start from 1, 1. So this 1, 2, 3, 4, 1, 2, 3, 4. We start from 1, 1. Maybe I label this in a different way, but it really doesn't matter. So suppose we use this plot according to this label. So suppose we start from x0 equals 1 and y0 equals 1. So what do we mean by randomly sample x1 given the current value of y, where y equals 1? So we sample this distribution. What do we mean that we sample from this distribution? It means that we randomly relocate this, this point, fixing y equals 1. So which means we randomly relocate within the first row of y equals 1. Okay, so you just randomly sample point in the first row. So this is a conditional sampling, which agrees with our intuition about conditional distribution, right? Okay, so that's the idea here. So you relocate within the row 1, and then suppose you get here after random sampling within this region. And then now you need to sample x1 equal to 3, right? And then because this is third column, and now you need to sample y1 from the conditional distribution y given the current value of x, which is 3, because you have updated x to 3. So that means you randomly sample a point in this column 3, so that, which means you randomly relocate in the column 3. And suppose you get here, then that means your y1 equal to 3. And then you relocate horizontally and then relocate vertically. So you keep doing that, always doing random relocation first horizontally and then vertically. And then after a lot of times, then your location become a random point within this unit square, so that the corresponding column and row become follow the joint distribution for xy. So that's the basic idea of the Gibbs sampler, which means you're just doing the random relocation. Okay, another example is like this. Suppose we have x and y. This is x, this is y. X is 1, 2, 3, 4. Y is 1, 2, 3, 4. But the partition look like this. So if you do this random relocation, eventually the point follow a uniform distribution within this supposedly unit square, and then it's more likely to get into this range, right? So this range actually has a maximum probability. So therefore, this sampling actually is similar to optimization. So in optimization, the corresponding algorithm is that instead of sample x given y, you optimize x given y. And then instead of sample y given x, you optimize y given x. So each time you choose the cell with a maximum probability. And then the algorithm reduced to the so-called coordinate ascent. So which means each step you just modify one coordinate. Okay. So the Gibbs sampler can be considered as a stochastic version for coordinate ascent. Okay, so now let's think about this population migration perspective, which is the most powerful intuitive way to think about the Markov chain. So that is, suppose you have 1 million people doing the same random walk, and in the first iteration, in the first step, they do random relocation horizontally in this row 1, right? And then in the second step, they do random relocation vertically. Okay, so here those points are randomly relocated here. Those points are randomly relocated in this second column, and here these points randomly relocated in the corresponding column. Okay, so you do this random relocation, and then you do this horizontal shuffling and the vertical shuffling. So you keep doing that, and eventually you will get to a uniform distribution over the unit square. And then if you continue to do the random relocation or random shuffling horizontally and vertically, you are not going to change the uniform distribution. So therefore, you are not going to change the distribution for XY, which are the rows and the columns. Okay, so that's the idea of the Gibbs sampler, how you visualize Gibbs sampler, and in particular, why it converges to the joint distribution of XY, because the points after this random shuffling horizontally and vertically will eventually come to a uniform distribution. At this stage, in the first iteration, even though you do this vertical relocation, this distribution may not be uniform at all. So you need to keep doing that until it reach the uniform distribution. Okay, so this is a population migration perspective. So at this stage, we say that XY follow the uniform distribution. It is stationary or equilibrium. Okay. And now maybe we can think about an example of a Gibbs sampler. So when we introduce a Gibbs sampler, we think about we have two random variables. But actually, for the Gibbs sampler to be useful, often they deal with a lot of random variables. And then they follow joint distribution, where the three operations for marginalization and conditioning and factorization still apply. So in the Ising model, maybe we can start from the one-dimensional one-dimensional space. So the idea is like this. Suppose the space is one-dimensional, and we have this 1, 2, 3, and m sites, and each site will have a electron which can either spin up or spin down. So if it is spin up, then xi equal to +1. If it is spin down, like this one, and then xi equal to -1. So this should be spin down. Little bit typo. And then we write our x. You can put an arrow here if you want, but in any case, we can write our x to be the spins, the collection, the spins at these m sites. So this is a physical model for the so-called ferromagnetic substance, where each site supposedly model an electron, and the electron can either spin up or spin down. But for us, we can think of we just want a joint distribution for those binary random variables. They are binary because they spin up or spin down, and just like the Gibbs distribution, so we write the joint distribution of x1 to xm as a Gibbs distribution, which means it is 1 over z e of negative epsilon x divided by t. So we use this distribution in simulated annealing for the traveling salesman problem. And here we follow the same recipe, where the energy is defined as a negative x1 times x2 plus x2 times x3 until, say, here we have xi plus 1, or xi minus 1, xi plus xi plus 1 until xi minus 1 times xm. So we just write this energy as a negative for summation of xi times xi plus 1 for I from 1 to I minus 1. So that is we sum over all the adjacent products. And this defines energy. Remember that the lower the energy, the more stable the system is, and the more probable this configuration is, right? So you see that here, because those are the spins, +1 or -1. So xi times xi plus 1 equals 1 if they have the same spin, and equal to -1 if they have different spin. So if this is -1, because the negative sign here, so which means the system, the energy will be high if the nearby spins are different. Okay, so therefore this energy actually prefers the nearby spins to be similar to each other. It doesn't matter whether they are positive or negative. As long as they are the same, then the energy will be low. So that's the Gibbs distribution. And it is in the form of 1 over z, which this is a normalizing constant or partition function, and e of negative epsilon x divided by t. Epsilon x is defined in this way. And if we let this 1 over t to be our beta, then we can write this as 1 over z, e of beta summation. So here summation I from 1 to n minus 1, xi plus 1. Okay, so this is the so-called Ising model. It is a very prominent model in statistical physics, and it is a model for modeling or explaining the ferromagnetism. And this is a distribution that consists of a lot of coordinates. So as I mentioned, even though we explain or we introduce the Gibbs sampler with only two random variables x, y, but the Gibbs sampler is the most useful when we have a lot of random variables. So for instance, if you have 100 random variables, then how many possible sequences you have, how many configurations you have, because for each xi, it has two choices, right? So in total, you have 2 to the 100 choices. So which means you have 2 to the 100 configurations. It is impossible to sample from such a distribution from such a large sample space directly. So therefore, we use the Gibbs sampler, which update the system iteratively. So each update only involve a small change. And in this case, we only change one coordinate, or we only change one site. So the pseudocode of the Gibbs sampler is like this. So we initialize this x randomly. So that is xi, each xi is obtained by a fair coin or from the Bernoulli distribution. From the random number perspective, you just randomly generate a number from 0 to 1, uniform random number. And if it is less than 1/2, you let xi to be -1. If it is bigger than 1/2, you let xi to be +1. So spin up and spin down. So this is just a random flipping as our initialization. And then we can iterate. So for each iteration, we can iterate 1,000 times, for example. For each iteration, we let I to go from 1 to n, say 100. And then we update xi given the current values of all the other components. So that is we update xi here, given all the values for the other coordinates. So each time you just change one coordinate. And this is doable and is feasible. So we can then keep doing this type of updating. And eventually, after, say, 1,000 iterations, we can then get a random sample from this Ising model. Okay. So now you see that again, for the MCMC, each step for this Markov chain Monte Carlo only make a minor or local or small change to the whole system or to the whole configuration. And here, each step only change one coordinate. And this is certainly much more feasible than sample the distribution directly, because the distribution is defined on 2 to the n possible values of x, right? So this is for m, even a moderate m, say m equal to 100. 2 to the 100 is already a astronomically big number. So we cannot sample from the distribution, the Gibbs distribution directly. Rather, we can use this type of coordinate-wise update or iterative conditional sampling to accomplish that. So each step, we only update one site or one coordinate, and we keep doing that. So eventually, this iterative algorithm will generate a configuration that follow the Gibbs distribution. Because originally, the Gibbs sampler was designed to sample from such Gibbs distribution. So it was called Gibbs sampler. Although the Gibbs sampler can be used to sample any other distributions. And again, here, we only need to know the distribution up to a normalizing constant. We don't need to know this z value explicitly. There may not be closed form of this z value. Okay, so again, just to emphasize that for this type of Gibbs sampler, just like any MCMC, so each step only involve a small change so that computationally it is very feasible. We can easily write the code in computer to implement such a step. And then we accumulate such updating so that we eventually get our result. So now how do we calculate the conditional distribution of xi given the values of all the other components? So here we use the notation x minus I to indicate the current values of all the other coordinates. Okay, so in order to compute this, we can still use the three operations that we studied when we studied two random variables. So we can easily generalize this to multiple random variables or multivariate random variables. So that is this one according to the rule of conditioning. So the conditioning operation, it will be this marginal equal to joint divided by the marginal. So the joint is xi, x minus I. So you can treat x minus I as a single random variable, even though itself consists of multiple elements, and then divided by the marginal of xi. Okay, and then the numerator, the numerator is still like this one, defined by pi x, the Ising model. So x and xi and x minus I together become the whole sequence of x1 to xn. And then this one, this is marginal. And recall that for marginalization, you only need to sum over all those the variables that are irrelevant. So here you see you marginalize over xi. So therefore, you sum over xi equal to positive 1 and xi equal to negative 1, and for the same x minus I, for the same values for all the other coordinates. So this is marginalization. Okay, and for the marginalization, so then you can see that the numerator is still like this one, and the denominator is like this plus this one. So here is actually here we also should use k because we fix xi, right, in this conditioning. So we better use x summation k from 1 to n minus 1, xk plus 1. The same like here and here. Okay, and when you look at this one, you will see that a lot of terms got cancelled because here we look at the xi, so we only need to look at xi. So you will see that this xi, so all the other terms, say x1 times x2, x2 times x3, all those things got cancelled. You eventually you only have xi minus 1, xi plus xi times xi plus 1. You only have these two terms left in this operation. So in the end, with a certain some calculation, you get this e of beta xi minus 1 plus xi plus 1. So this is I plus 1 is a subscript. This xi minus 1 also subscript, just like here. Okay, and then e for beta. So in this case, we have xi, what's the probability, say xi equal to positive 1, spin up. And then we plug in positive 1, so we get this term. And then we have this positive 1 here, and then negative 1, right? Because here we add up xi equal to positive 1 and xi equal to negative 1. So for the negative 1, we have negative here, beta and this one. So this is just some tedious calculation. If you really write this out, you will get this form, which means we also have a Markov property here. So that is the conditional distribution for xi only depends on xi minus 1 and xi plus 1. That is the two nearest neighbors. Okay, and then you get the probability that xi equal to positive 1 given the current values for all the other components, which only depends on the current values of the two neighbors. So let's call this as our probability P, and then we can flip this xi by generating a uniform random number from 0 to 1. So if it is less than p, we assign xi to be positive 1. If it is bigger than p, we assign xi to be negative 1. So it's very much like you flip a biased coin with a certain probability computed from this formula, which only depends on the two nearest neighbors. Okay, so this is the idea for the Gibbs sampler, and you then go through all the size for I from 1 to n. So you update each one conditioning on all the other values, which means conditioning on its two nearest neighbors, and keep doing that. And after, say, 1,000 iterations, the current configuration can be considered as a random sample from the target distribution, which is the Ising model. Ising model is a Gibbs distribution, and then we call this algorithm the Gibbs sampler. Okay, so this is a example of Ising model in this one-dimensional situation. And in the two-dimensional space, so we have a grid, say this time m times n grid, and then each grid is xij. It can be spin up or spin down, and then we can still use the Gibbs sampler to sample from the corresponding Ising distribution. And this type of Gibbs sampler is called heat map, heat bath. So that is you put the system in an environment, so the system interact with its environment. And here, actually, you can see that if you want to update this one, so if you update this one, it has 4 nearest neighbors, right? You need to use the values of 4 nearest neighbors in the two-dimensional situation. But if you update this one, it has a neighbor here, but it should also have neighbor here and neighbor here. So that is, you need to provide the boundary condition. So suppose all the boundary values are positive 1. Then it is like you put this system in the environment where those are the positive value. You have positive values or positive spins for the electrons. And you can also put this as a negative 1. So all the values are negative 1. So this actually is used to explain the idea for spontaneous magnetization. So for example, if you put iron close to a magnet, then the iron will acquire the magnetization spontaneously. The reason is that even if this system is very big, but if you change the boundary condition from, say, all positive 1 to all negative 1, you are going to change the distribution dramatically. So this is the idea for so-called phase transition, and this can be used to explain that why a piece of iron can acquire magnetism spontaneously, because based on the boundary condition does not wash away, does not vanish, even though the system becomes bigger and bigger. Okay. So this means that can only happen below a certain temperature, or when this beta parameter in the previous page is big enough. Okay, so that is at a low temperature, things can happen. Things like that can happen. So that is, if you have the positive ones on the boundary, then most of the xij will be positive 1. And if you have negative ones on the boundary, and if you do keep sampling, you will see most of the values will be negative 1. Okay, so it doesn't like half of them will be positive 1, half of them will be negative. So that is the boundary condition does not vanish even if the system becomes bigger and bigger. So that can be used to explain the phenomena of a spontaneous magnetization, which is a special case for the phenomena called phase transition, which is a key phenomena studied by statistical mechanics. For example, there can be the coexistence of water and ice. So they are described by the same model, but just because the change of the boundary condition, then you get two different, totally different distributions. So this is a statistical explanation. So the physical phenomena actually has a statistical or probabilistic explanation. Okay, so this is an example of two-dimensional Gibbs sampler. In fact, you can go to YouTube and search the Ising model or simulation of the Ising model, and then you will see some videos about the simulation of the Ising model using this heat bath, not heat map, but heat bath or Gibbs sampler algorithm. So we have studied the discrete case, and now we can also move to the continuous case. So following the teaching of Newton, whenever we want to study something continuous, either in continuous space or continuous time, we can always discretize the space or time into something like infinitesimal small intervals or infinitesimal small cells. For example, here we can discretize the value of x and y so that this part, this column, correspond to x plus delta x, and this row correspond to y plus delta y. And then we can again think about the probability for the points fall into x to x plus delta x, y to y plus delta y, like this one, right? Or the conditional distribution that y is in this range, y belong to this row, given that x belong to this column. So everything follow in the same way as the discrete case. So that's how we jump or move from the discrete situation to continuous situation by discretizing the x and y. So we discretize the continuous variables into discrete intervals or discrete cells like this. So, but remember that this is just how we label those intervals. We label these intervals for x plus delta x. But remember, this is still in the range of U1, U2. We are still talking about the unit square, so that the different cells have different probabilities. But then we can actually think of a map or translate those points into the domain of xy. So originally those points are in this U1, U2 in the unit square, but we can translate this into domain of xy so that those points become the points in this domain according to the mapping effected by this labeling for those row and column. And then now after in this domain, then this row and column become regular, right? More regular. So in the xy domain, because this is in the xy space instead of u1, u2 space. So in the xy space, you have this column and row, right? And then we can still think of, say, the probability and the conditional probability based on this frequency or relative frequency. So by the same logic, basically. So that is, we can think of for how often the points fall into this range, which means how often the point fall into this cell, which means how often the points fall into this regular cell. So the size in this xy domain, the size of this cell is delta x delta y, and then the proportion of the frequency of the points belong to this small cell will be the density times delta x delta y. Or in other words, the density, probability density will be the probability of the frequency in the long run frequency of the points belong to this cell divided by the area of this cell, which is the notion of the density. And therefore the probability of the frequency is f of xy delta x delta y. So this is actually correspond to pxy in the discrete case. So therefore, we can just apply the three operations also to the continuous case. So for example, marginalization. So what's the frequency or what's the probability that the random point belong to a certain column, either on this plot, this column, or correspondingly this column. All right, this can be equal to what? The density of x times delta x, because this we look at the marginal, right? The marginal, the size of this is delta x, and then this equal to what? We just sum over all those cells, sum over all the y. So that will be summation y, and for each one, the frequency of the points or the area here is actually fxy delta x delta y. Okay, and then we sum over all y. So now you see delta I got cancelled. So then you have the marginal distribution of x equal to when delta y go to 0, this become an integral, right? Sum become integral. And then you have this result so that it is the joint and the dy, fxy dy. Similarly, the marginal distribution of y is the integration of joint fxy over dx. And you can also study this conditional distribution of y given x. So here we look at the conditional distribution of y, where x is fixed at this x. So this is density multiplied by delta y, we get the probability. This corresponds to py given x. Because this is density, you always multiply whatever for this variable you consider, right? And this can be written as the joint probability divided by the marginal probability. So joint probability is the density times delta x delta y, and the marginal probability is density times delta x. Okay, so this formula corresponds to the formula where py given x equal to pxy divided by px. So this is px, this is pxy. So pxy, that is the probability of this cell, is the density times delta x delta y. And similarly, the probability of that column is the density times delta x. Okay, so essentially this tells us what the probability y belong to this this range, given x belong to this range. Okay, and now you see that the delta y get cancelled, delta x delta get cancelled, so that the conditional equal to joint divided by the marginal. This is actually the same as the discrete situation because delta x got cancelled, delta y also got cancelled. And then from here, again, we can also derive factorization. If we multiply both sides by fy, you see fxy equal to fy times fx given y. And by the same logic, it also equal to the marginal x times f of y given x. So this is factorization. And at this point, we may think of playing with the Gibbs sampler by sampling from the bivariate normal distribution. So for bivariate normal distribution, x follow normal 0, 1. This is standard normal. Then you see that the marginal distribution of x is like this one, 1 over square root 2 pi e of negative x squared over 2. So this is the density for the standard normal. And for the bivariate normal distribution, y given x equal to this fixed x is a normal distribution with mean rho times x, where rho is a correlation parameter and variance 1 minus rho squared. So rho is given for the bivariate normal distribution. So this is just a special case of a more general normal distribution, normal mu sigma square, where mu equal to rho x and sigma square is 1 minus rho squared. So this is how we define bivariate normal distribution. In fact, based on this definition, clearly we can sample from bivariate normal distribution directly without using Gibbs sampler. So we can just sample x from normal 0, 1, and then given the value of x, we sample y from this more general normal distribution, whose mean and variance depends on this x. Again, rho is given. Okay, so we can do this direct sampling. But suppose that we want to use Gibbs sampler to sample from it just for fun. So this example is not as real as Ising model. There's no other good methods to sample from Ising model, but for bivariate normal, we can sample bivariate normal directly by sample x and then sample y given x without resorting to the Gibbs sampler. But here, I just want to use this as illustrative example that we can play with the Gibbs sampler as a toy example. Okay, and this example can then be generalized to other examples. And recall that we now have the marginal of x, and based on this one, using the general form of the distribution, general form of the density of a normal mu sigma squared, we can also write down the conditional density of y given x, which is like this. So the conditional density is like here, y given x. So it's 1 over this is just a normal density, 1 over square root 2 pi sigma square. Sigma square is inside of square root. E of negative, there should be a negative y minus minus mu squared divided by 2 sigma squared, which is if we plug in sigma squared, which is 1 minus rho squared. So this 1 over square 2 pi, and the 1 minus rho squared, and the e of negative y minus mu equal to rho x. And then sigma squared is 1 minus rho squared. So we just plug in rho x and y minus rho squared as mean and variance respectively. So a illustrative example for a bivariate normal is like this. Okay, so this is y equal to rho x. This is called regression line. Regression because rho is less than 1. And for this regression line, so it gave us a mean. So given x at this range, okay, in this slice, if you look at the distribution in this slice, it's centered. There should be some points here. It's centered at rho x, and the variance is 1 minus rho squared. So therefore, as rho goes to 1, then the variance, which is 1 minus rho squared, goes to 0, so that the variance becomes very small. So effectively, those points are very close to this line, which is y equal to rho x, where rho is close to 1. Okay, so this rho is called correlation. The bigger, the correlation is always a number from -1 to 1. So the sign of this rho indicate whether it's a positive relationship or negative relationship. And the magnitude of this rho, whether it's close to 1 or not, in absolute value, indicate how strong the linear relationship is. Okay, so this is the idea of the Gibbs sampler. And then now we obtain f of x and fy given x. So we only need to multiply them together. So this will be 1 over square root 2 pi e of negative x squared over 2. So that's a marginal of f of x. And then we multiply by the conditional of y given x. And then we get this expression. And with some calculation and regrouping, we get this form. 1 over 2 pi square root of 1 minus rho squared, and then e of negative x squared plus y squared minus 2 rho xy divided by 2 1 minus rho squared. So here you see that this is symmetric in xy. So if you exchange the rho of xy, you are going to get the same value, same density. So therefore, by the same token, then the conditional distribution of x given y, which can be denoted as x given y equals y, is also like normal with the mean rho y and variance 1 minus rho squared. So that is if we know the density for the bivariate normal, and then we know the conditional distribution of y given x, and we also know the conditional distribution of x given y, so that we can play with the Gibbs sampler. Again, this is a toy example because we can sample from bivariate normal distribution directly without the iterative Gibbs sampler. But suppose we want to play with the Gibbs sampler, we can then use this algorithm. We iterate at x0, y0. For example, x0 is 10, y0 is a negative 10. And we just use arbitrary value, and then we iterate. So we sample xt from the distribution for x given the current value of y, which is yt minus 1. So it is normal rho yt minus 1, variance 1 minus rho squared. And this can be written as rho yt minus 1 plus square root of 1 minus rho, and then normal 0, 1. So normal 0, 1 has mean 0 and variance 1. So because it has mean 0, if you add rho yt minus 1, it has mean or expectation rho yt minus 1. And this guy also has a variance 1. So if you multiply this by square root of 1 minus rho squared, then because variance is on the square unit, so the variance of this whole thing will be 1 minus rho squared. Okay, so this is how we generate from such a distribution. You can first generate a normal random variable and then multiply this by square root of 1 minus rho squared, and then add rho times yt minus 1, and then you generate xt. After that, you then generate yt. So this is typo. This should be yt. Yt is generated from normal of rho and then current value of x, which become xt because you have updated xt, and the variance 1 minus rho squared. So this again can be written as rho xt plus square root of 1 minus rho squared normal 0, 1. This normal 0, 1 is independent of this one. Okay, so that's how we generate yt. This is yt. And then we just keep iterating. And then we eventually xyt will follow by very normal distribution. So in the final exam, I asked you to implement a R code for carrying out the Gibbs sampler for sampling from bivalent normal. So supposedly we know the joint density of bivalent normal, which is here, and then we know the conditional distribution of x given y and y given x. And then we can use this iterative conditional sampling to carry out the Gibbs sampler algorithm. So this is sampling from the normal distribution of bivariate continuous distribution. So I can also give you a similar intuitive example to illustrate why Gibbs sampler works. So the idea is like this. Suppose this time we make things simpler. Our joint distribution, instead of bivariate normal, it follows a uniform distribution over this certain shape. So it's similar to bivariate normal. Okay, so we want to sample from the uniform distribution over this omega, and omega as a sample space has this peculiar shape. And then suppose we start from here, a random point, start from an arbitrary initial value, and then when we sample y given x, it actually means that we fix y, we change x, because it is uniform distribution. So we sample uniform distribution from this line. Okay, suppose we move here, and then we sample y given x, which means we fix x, we change y. Again, because this is uniform distribution, we then sample from the uniform distribution of this vertical line. So therefore, if you think about the population migration, suppose you have 1 million points, then in the first step, you relocate, resampling this 1 million points on this horizontal line, and then you get those different positions. And then for each point, you resample it as uniformly from the corresponding vertical line and then the horizontal line. So you keep doing this horizontal shuffling and vertical shuffling, similar to the discrete case. Then you can eventually get uniform distribution within this omega. And then if you do this vertical shuffling and the horizontal shuffling, you are not going to change the uniform distribution. So that will be our stationary distribution. So this is a visualization for the Gibbs sampler for this continuous case, which actually also applies to the bivariate normal distribution. So you can think of a population of points, right? And if you do the reshuffling, according to the conditional distribution, you are not going to change the overall distribution. So that's the basic idea. And then so after we implement the Gibbs sampler or maybe Metropolis algorithm, and then we can use the Gibbs sampler or Metropolis algorithm to do this Monte Carlo integration. And so suppose we want to say estimate a integral, which is expectation for pi according to pi of h of x. So this capital X follow the stationary distribution pi. Then we need to draw sample from pi. And for the Monte Carlo integration, so the requirement is we should draw sample from pi. But if X is very complex, it may be difficult, right? And then you run MCMC, either Metropolis algorithm or the Gibbs sampler to generate a sequence of values, okay? And each time you just make a small change, a local update, and you keep accumulating. And then you do this for a lot of iterations. So you should have a burning period, x1 to xb, and then you throw them away. So that is xb may be considered to be approximately follow pi, and then the rest will also follow pi. And then you have a sequence of samples that sampled from pi, although the sequence are not independent anymore. They are dependent, right? Because this one depends on this one, and the next one depends on this one. So there's actually often partial correlations. But nonetheless, each one is a sample from pi. So therefore, you can still use those values to do Monte Carlo integration, which means you use sample average to approximate the expectation. So that I hat is you sum over I from b plus 1 to t h of xi. So you use those things after throwing away, discarding the burn-in period. And then the number for values you have is 1 t minus b. So you got 1 over t minus b. So this is a sample average. And for this sample average, because each value follow pi, so the expectation of average is average of expectation, no matter whether they are correlated or not. So therefore, we still have E of I hat. So as this is random, right? Because suppose each one of you run MCMC, you are going to have different samples. So you're going to have different I hat. So this I hat fluctuates around the true value of I. It is unbiased estimate. But the variance of I hat can be bigger than the variance of I hat for independent samples, because now running a Markov chain, you have dependent samples. The subsequent configurations only amount to minor change. So there's a lot of positive correlations or covariance among those values. So if you look at the variance of sum, it will be the sum of the variance plus all those covariance, 2 times the covariance. So therefore, the overall variance can be much bigger because of these Markov chain dependencies. Nonetheless, we can use MCMC to do Monte Carlo integration if the distribution, target distribution pi, is very difficult to sample from directly. Okay, and we can either use Metropolis algorithm or use the Gibbs sampler. In fact, the Gibbs sampler has the same spirit as the Metropolis algorithm, in that each step we only make a minor change. And in the traveling salesman problem, we just randomly select 2 cities, we exchange their order. But in the Gibbs sampler, we just, because it is a vector or it is a multi-component or multivariate random variables. So each time we only need to update one coordinate. And you can think of the Gibbs sampler, this conditional sampling, as a special case of the proposal. So you update this, you propose to update a particular coordinate based on its conditional distribution, given the current values of all the other coordinates. And this proposal distribution is very special because if you do some calculation, you will see that you will always accept it. So it is a proposal with acceptance probability 1. So in that case, you can think of Gibbs sampler as a special case for the Metropolis algorithm. But in either case, you can use MCMC to do Monte Carlo integration in the case where this pi cannot be sampled directly. And a very commonly applicable scenario is Bayesian statistics, where we often need to use MCMC to do the Bayesian calculation. So in Bayesian statistics, the basic idea is that you may have a unknown parameter theta. It follows a prior distribution. And then the data x given theta follow the conditional distribution. This is often called a statistical model with unknown parameter theta. Theta may be multivariate. You may have, this theta may have multiple components or multiple coordinates. And based on these 2 assumptions, the prior and the conditional, you get the posterior distribution of theta given x. So this posterior distribution is a basis for us to make inference about unknown parameter theta. And in order to calculate this, we use this conditioning operation. So that will be the joint divided by the marginal, right? And then we use factorization to factorize the joint into p theta, p x given theta. So that is marginal times conditional. And then this px, we can obtain px from p theta x by marginalization. We integrate out theta. So we integrate out theta because this numerator become this one, right, according to factorization. So this is actually the base rule. And then we can use the base rule to calculate the posterior distribution of unknown theta given x. And all our inference about this theta, including, say, a point estimate or uncertainty estimate, can be based on this posterior distribution. And this posterior distribution can be, if we want to compute some posterior expectation or expected value of some quantities with respect to the posterior distribution, you can then use MCMC to sample from this posterior distribution. Okay. And that's the main calculation tool in the Bayesian statistics. You use MCMC to sample from the posterior distribution. And then in this posterior distribution, you only need to know P theta and Px given theta, which is given right here. And you don't need to know the denominator, which can be considered as a normalizing constant. So as long as you know P theta and Px given theta, you can then use MCMC to sample from the posterior distribution of theta. So this actually has a liberating effect. So when you do Bayesian statistics, you just specify a prior. You often, this is very diffused, quantify your ignorance or uncertainty, and then you specify the model, how the data generated given the fixed value of theta, and then you can get the posterior, which is proportional to the numerator, which is here, and then you can use MCMC to sample from it. So that make Bayesian statistics almost automatic. So you only need to specify the prior and the conditional of the generation model. So here, why people call this Bayesian as if it is a religion? Because it is based on the idea that if you don't know something, then you put a prior distribution to quantify your uncertainty or ignorance. And then you treat something unknown as a random variable, and you use the distribution of this random variable to quantify your uncertainty. So this actually is something a little bit controversial in the sense that if something we don't know, for example, the speed of the light in this universe, if we don't know this number, whether this number is random, in what sense it is random. So that actually is debatable. So the frequentist point of view is that if we don't know the speed of light, we just think of this as unknown constant. We don't think of this as a random variable, as if there's multiple universe, right? Then there's some repetition. You can then see the density of frequency in the sense that the randomness can be expressed as in terms of the frequency. So that people don't believe that. So we only have one universe. We only have one unknown constant, which is the speed of the light. Why should you treat this as a random variable and put a prior distribution? But Bayesian said that if you are subjectively uncertain about something, and then you can always use a prior distribution to quantify your ignorance or uncertainty, and then you use this Bayesian framework to do the calculation, including MCMC sampling. Okay, but in any case, this is just a perhaps the most important use case for MCMC, and Bayesian statistics itself is deserve a special course. So therefore, I will not get into too much detail in it. Except that nowadays in machine learning, people actually accept this point of view. And in fact, if theta is high dimensional, you really need to put a prior distribution. And this prior distribution is like an inductive bias. And it is related to the so-called regularization in machine learning. So those things are actually very consistent with each other. So people do not really argue too much about this Bayesian formulation nowadays. So I think I have go over two key algorithms for MCMC, the Metropolis algorithm and the Gibbs sampler. In particular, the Gibbs sampler is a stochastic version of coordinate descent. So each step, you just optimize over one coordinate while fixing all the other coordinates. But then we also know that we can use gradient descent to minimize a function. So what's a stochastic version of it? There is also a stochastic version for gradient descent, which is called Langevin dynamics. So if you want to minimize or sample from a Gibbs distribution, you can run a gradient descent step on the energy function, but you can also add a small Gaussian or normal distribution, a normal random variable to account for this uncertainty or to add the randomness in the sampling. So Langevin dynamics is the stochastic version of gradient descent, just like a Gibbs sampler is a stochastic version of coordinate descent. So the Langevin dynamics, and later there's also a Hamiltonian Monte Carlo, are all based on the gradient of the energy function. And it can be very useful in the continuous case. So if you are interested, you can search for the related literature. But in this class, we don't really have much time to study Langevin dynamics and Hamiltonian Monte Carlo. But I think by studying Metropolis algorithm and the Gibbs sampler, we already get the essence for Markov-Chain Monte Carlo. So in the final exam, it will be focused on this implementing Markov-Chain Monte Carlo, in particular, the traveling salesman problem and the very normal sampling. So I think for these 12 lectures, I just try to give you some basic ideas or methods for MCMC. And along the way, I also try to warm up your understanding of probability theory, especially from a intuitive perspective. And because, as I said before, Monte Carlo method is almost like a probability in action. So I hope that in this course, you'll gain a better or more concrete grasp for those concepts and theory in probability. And also by doing your homework and running the R and the Python code, you also gain some hands-on experience for the Monte Carlo methods. I hope that this course will be useful for your future study or your future career. And in this, for this sequence of videos, I just go over the notes taken by Grace. So I also want to thank Grace for the meticulous note taking. Although there's some typos, this I hope I hope that everyone can understand that when you attend a lecture and trying to write things down, there can be typos, and some of the typos are caused by myself. So when I explain the notes, I always emphasize on those places where there are typos. So I hope that this won't has any effect or impact on your learning experience. So yeah, in any case, I hope that these 12 lectures capture the essence of Monte Carlo methods, including random number generators and Monte Carlo integration, including importance sampling, and finally Markov-Chain Monte Carlo. Okay, I think that's it. Thank you very much for your attention.